we're going to take a look at inverse trig functions. So let's start with our function y equals sine x. So this is a function that you've seen before. X here is our angle, and y here is our ratio, the opposite over hypotenuse ratio in our triangle. So we got a function y equals sine x. If we're going to find the inverse of that, well then y becomes x and x becomes y. And now, to isolate y, if we're going to isolate y here, we're going to take the inverse sine of both sides to get rid of that. And so we would get y equals the inverse sine of x. Or in other words, would look like this. So y equals sine x and y equals inverse sine of x are inverse functions of each other. Sometimes this function here is called this, arc sine of x. You won't see this that often, but arc sine really means inverse sine of x. I'm going to stick with this sine minus 1 notation here for inverse sine of x. So now x has become a ratio, and over here y has become an angle because we now have the inverse of it. X and y have gotten switched. Let's see how this would look graphically. Okay, I'm going to draw them on separate graphs here, but we're going to graph y equals sine x, and then we'll graph the inverse y equals inverse sine of x. So you remember that sine x goes to the point 0, 0, and let's see, what should I do here? Let's make this pi over 2, and this pi, 3 pi over 2, 2 pi, and we'll maybe make this 1 here and this minus 1 here. So we'd have a dot here, here, 0, and the graph would look something like this. So this is the graph of y equals sine x. Well, if we take, let's just even take these values right here, these 5 points, and plot their inverses. So remember, the inverse is switching x and y, so 0, 0 is still going to be 0, 0. Now we're going to have, instead of the point pi over 2, 1, we're going to have the point 1 pi over 2. So we're going to basically swap our scales around here. Which is kind of why I chose to do it on a separate graph. Okay, so 0, 0, pi over 2, 1 becomes 1 pi over 2. Pi 0 becomes 0 pi. 3 pi over 2, negative 1 becomes negative 1, 3 pi over 2. And 2 pi, 0 becomes 0 and 2 pi. And so we had a graph like this. And if we continued this half of it, the graph would do this sort of thing. So can you see what the problem would be with this? Y equals inverse sine of x. It doesn't pass a vertical line test. So this is not a function. And if you think of all of the trig functions, so here's your sine graph, the original sine x graph does not pass the horizontal line test. That tells us that it won't pass the vertical line test. The inverse will not pass the vertical line test. You think of the cosine graph, that would do this sort of thing too. It's not going to pass a horizontal line test. So if we take the inverse of it, it won't be a function on this entire domain. Same thing with y equals tan x, which kind of does this thing. Does those periodic functions. It won't pass a horizontal line test. None of the 6 trig functions, sine, cosine, tan, cosecant, secant, and cotangent, none of them will pass a horizontal line test, which means none of the inverses will end up being a function. So what mathematicians have had to do is they've had to restrict the domain of sine x so that the inverse, y equals the inverse sine of x, will be a function. And so what they've done is they've said y equals the inverse sine of x will be defined to be this function right here. It goes from -1 to 1 on x, and it goes from -pi/2 to pi/2 on y. And if it goes any farther past that, it's going to start curving around here and going to start curving around here and not be a function anymore. So if we take the original sine x graph, back to a red pen here, and restrict it, if we restrict its domain from -pi/2 to pi/2, then the inverse sine of x will be defined. This function here, when we take the inverse of it, will give us y equals the inverse sine of x, which will be this function right here. So here's the graph of cosine x. We know it starts at 0, 1, comes down to pi/2 to pi to 3 pi/2, goes this way as well. Well, keeps doing these curves like this. It's not going to pass a horizontal line test. So in this case, if we're going to graph the inverse, it is defined to be the cosine graph that goes from 0 to pi. So if we just take that domain, then when we graph the inverse of it, it shall be a function. This is the point 0, 1. So we will have, we will have the point 1, 0. This is the point pi/2, 0. So we will have the point 0, pi/2. And this is the point pi -1. So we'll have the point -1 pi. And it will look a curve like this when we sketch its inverse. So this would be the graph of y equals the inverse cosine of x. So this cosine x graph is defined to be 0 to pi so that the inverse cosine can look like this. So then, just to summarize here, I won't show you the graphs for the inverse tan and the inverse secant x, and we won't worry about inverse cotangent or inverse cosecant because those functions don't appear that often. But if we're looking at the function y equals the inverse sine of x, it is defined to be the inverse of y equals sine x on this domain from -pi/2 to pi/2. And the inverse cosine x will be the inverse of y equals cos x from 0 to pi. And the inverse tan x would be the inverse of y equals tan x on the domain -pi/2 to pi/2. And the inverse secant x is the inverse of y equals secant x on the domain 0 to pi. So it's important to know that these are the restrictions on the domains of these functions. So these inverse functions end up being defined, end up being functions. So let's do some inverse trig calculations here. And this is really things that you've done before. Only what we have to make sure is we have to make sure that we are restricting the domain so that it satisfies these conditions here. So let's do the inverse sine of 1/2. So remember, we take the inverse sine of ratios. So these are ratios. The sine ratio is positive. So you remember back to this. All students take calculus. Sine was positive here and here. Well, when we're dealing with the inverse sine is only defined between -pi/2 and pi/2. So we can only look at angles between here and here when we're talking about the inverse sine. And that's okay because all of the positive angles, or sorry, all of the positive ratios will take care of in this quadrant, and all of the negative ratios will be taken care of in this quadrant. So the quadrant is going to be quadrant 1, and you think back to the ratios, your special triangles, where this is pi over 3 and this is pi over 6. So what is the angle what is this angle where the sine ratio is 1/2? Sine's opposite over hypotenuse. So this would be pi over 6. The sine of pi over 6 is 1/2. So the inverse sine of 1/2 would be pi over 6. It's true that there is another angle over here, which is 5 pi over 6. That's true as well. But 5 pi over 6 is not in the domain of this inverse sine function. So pi over 6 would be our angle there. The inverse cosine of -1. So cosine is defined on the interval 0 to pi. So you think of your cosine graph, which looks like this. We want to know, where is cosine -1? Cosine is -1 right here at pi. So what is the angle? The angle is pi. The cosine of pi is -1. Here we have the inverse sine of -√3 over 2. Well, we know that sine is negative in this quadrant, and it's also negative in this quadrant, but we can't use these quadrants for inverse sine. Again, remember what the domain is from -pi over 2 to pi over 2. So it looks like we're going back to this ratio again. Pi over 3. The sine of pi over 3 would be √3 over 2. So going this direction, pi over 3, means that the inverse sine of -√3 over 2 is -pi over 3. The inverse tan of 1 over √2. This is a positive ratio. Tan is normally positive here and here, but checking back here, inverse tan is only defined from -pi over 2 to pi over 2. So that means only the angles in quadrant 1 and 4. So that means we're looking for the angle in quadrant 1. That gives us a ratio of 1 over √2. That would be this triangle. And that's not going to work. So let's make this a ratio of 1. There we go. So the tan of pi over 4 is 1 over 1. So the inverse tan of 1 would be pi over 4. Pi over 4 is the angle that gives us a ratio of 1. Inverse secant of 2. So secant theta is the reciprocal of cosine. So secant is positive the same place that cosine is positive in. See, from 0 to pi is the same domain as the inverse cosine. So we can use this quadrant or this quadrant. Cosine is positive in quadrant 1. So we'll be using the angle in quadrant 1. And going back to our triangle, which one gives us a secant ratio of 2? That would be pi over 3, because a secant ratio is hypotenuse over adjacent. So pi over 3 becomes our angle here, and that means that the inverse secant of 2 would be pi over 3. Pi over 3 is the angle that gives us a secant ratio of 2. So the only thing that's different maybe than what you did before when you were finding angles is we got to make sure that the angle fits within the restrictions of the domains of these inverse trig functions. We could also look at doing questions like this. What is the inverse sine of the sine of 6 pi over 7? And then we'll also look at what's the inverse cosine of the cosine of 5 pi over 3. So we're going to take, here's what we know. We know the angle, because we're taking the sine of this, so this must be the angle. The angle is 6 pi over 7. That would be right here. 6 pi over 7, so it'd be in quadrant 2 with a little reference angle here of pi over 7, because this would be pi here. So we are in quadrant 2. This angle given is in quadrant 2. So we're going to take the inverse sine. In other words, we need to know what is the ratio. This would be the ratio here. What is the ratio when we take the inverse sine of that? What angle does that produce? So we need to go back and look at where inverse sine is defined. Inverse sine is defined between negative pi over 2 and pi over 2. That means whenever we take the inverse sine of this ratio, we have to get an angle somewhere in here, from negative pi over 2 to pi over 2. Well, here's what we know. We know that sine is positive in quadrant 2. So where else is it positive? It's positive in quadrant 1. So we can get the exact same angle. So if this angle here is pi over 7, we can get the exact same angle in quadrant 1. That's going to give us the same ratio. You can see that. The opposite here is going to be identical to the opposite here, and the hypotenuse here is the same as the hypotenuse here. So instead of 6 pi over 7, which would be undefined in the inverse sine function, we can say this is exactly the same as the angle pi over 7. So the sine ratio of 6 pi over 7 is going to be identical to the sine ratio of pi over 7, or 1 pi over 7. So basically all this is a matter of figuring out which angle, which quadrant does this angle end up in, and then finding the exact same angle, the exact same ratio in either quadrant 1 or quadrant 4, because that's where sine's defined. If we look at this one, we're asked to find the inverse cosine of something. Inverse cosine is defined between 0 and pi. So that means our answer is going to have to be somewhere between 0 and pi. And we know cosine is positive here and it's negative here. So this would be all of our positive ratios. This would be all of our negative ratios. The angle that we're given is 5 pi over 3. That would end up being about here, 5 pi over 3, because that's 1 2/3 pi. So then the little reference angle in here is going to be pi over 3. In this quadrant, all students take cosine is positive. So the quadrant where it's defined, where it's also positive, would be quadrant 1. So if the reference angle here is pi over 3, then the exact same ratio will occur in quadrant 1 with the reference angle of pi over 3. My sketch is not very good here, but let's make that a little bit more similar to that. There we go. So if this angle is pi over 3 here and this angle is pi over 3 here, the adjacent and the hypotenuse are going to be identical. So it's going to give us the exact same cosine ratio. We got a positive x value here and the hypotenuse, and a positive x value here and the hypotenuse. So the answer to this question would be pi over 3. Cosine of 5 pi over 3 would be some ratio. The inverse cosine of that will put us back into quadrant 1, because that's where the inverse cosine is defined. And finally, we can also look at questions like this, where we're not given a specific ratio. So this would be a ratio here, because we take the inverse sines of ratios, and we want to find what is the cosine of the inverse sine of x. So x would be a ratio. When we take the inverse sine of x, that's going to give us an angle. And then we're asked to find the cosine of this angle theta. Well, cos theta is going to be the adjacent over the hypotenuse. So maybe with these ones, it's probably easiest to sketch a little picture. So there's some angle here, theta, that we don't know. We're not given the angle. What we are given is the ratio, the sine ratio of that angle. So sine we know is opposite over hypotenuse. So maybe the best way of writing this is to write it like this, because the ratio is always something over something. So x must be x over 1. So x must be the opposite and 1 must be the hypotenuse, because it's a sine ratio. So opposite must be x and hypotenuse must be 1. So here's our little sketch. The inverse sine of x would be theta. So here's theta. Now the question wants to know, what is cosine of theta? So what is cosine of theta? Well, that's going to be adjacent over hypotenuse. The problem is we don't know what this side is. But it's a right triangle, so we can use Pythagoras' theorem. We'll call this, I don't know, let's just call that L, because we don't know what that is. So L squared plus x squared equals 1 squared, which is 1. So L squared is equal to 1 minus x squared. L is equal to the square root of 1 minus x squared. So now let's replace this. And now we can answer the question, what is cosine of theta? Cosine of theta is adjacent over hypotenuse. So root 1 minus x squared over 1, which is just root 1 minus x squared. Let's look at another one of those. How about we do, well, we can make up any one really. How about we do tan of inverse secant of x. So this would be the secant ratio, because we take inverse secant or inverse tan, whatever, of ratios. So these are ratios here. So in a triangle, the secant ratio, which is, so secant is the reciprocal of cosine. Cosine's adjacent over hypotenuse, so this must be hypotenuse over adjacent. So here's our angle theta. Secant is hypotenuse over adjacent. So this must be x and this must be 1. And now we have in our little sketch theta right here. And we have to find tan of theta. There we go. Tan theta. So tan is opposite over adjacent. So again, we don't have this side, but we can find it. It would be the square root of x squared minus 1. So the tan theta would be root x squared minus 1 all over 1. Oh, it's not exactly the same as last ratio there, but similar. Root x squared minus 1. We'll look at one more example here. How about we do the tan of the inverse sine of x. So x is our ratio. There's some angle then theta where the sine ratio, which is opposite over adjacent, sorry, opposite over hypotenuse, so this must be x, this must be 1, because the ratio x is like x over 1. And tan, so now we've got our expression for theta here. And we've got to find tan theta. So tan is opposite over adjacent. So that must mean, using Pythagoras' theorem, that this side is 1 minus x squared. So the tangent of theta is x over root 1 minus x squared. So there's just some of the things that we can do with inverse trig functions and some of the identities and properties of inverse trig functions.